Picture this. You're standing in a vast cathedral of knowledge, and towering above you are two magnificent pillars that hold up our entire understanding of the universe. One pillar gleams with the pure light of relativity, carved from Einstein's revolutionary insight that nothing can travel faster than light. The other pillar pulses with the mysterious force of gravity, sculpted from the mind-bending idea that massive objects actually warp the very fabric of space and time itself. These two pillars have stood strong for over a century, supporting nearly everything we know about physics. But here's the problem that keeps physicists awake at night. These pillars don't quite fit together. They're made of different materials, built with different blueprints, and when you try to connect them, cracks appear that threaten to bring down the entire structure. Let's start with the pillar of relativity. In 1905, Albert Einstein dropped a bombshell on the scientific world. He showed us that the speed of light, roughly 300 million meters per second, isn't just fast. It's the ultimate cosmic speed limit, woven into the very fabric of reality itself. Nothing with mass can reach this speed. Nothing can exceed it. This isn't just a rule. It's the rule that governs how space and time work together. Einstein's special relativity revealed that as you approach light speed, time slows down, distances shrink, and reality becomes increasingly strange. Then came general relativity in 1915, which showed us that gravity isn't really a force pulling objects together. Instead, massive objects like stars and planets create curves and dips in space-time, and we experience this warping as gravity. Think of it like a bowling ball placed on a stretched rubber sheet. The ball creates a depression, and if you roll marbles nearby, they'll curve toward the ball. That's essentially how the Sun keeps Earth in orbit. Our planet isn't being pulled by some invisible hand, it's following the curved path that the Sun's mass creates in space-time. Now, let's examine the other pillar, quantum mechanics. This theory emerged in the early 1900s as scientists tried to understand the behavior of atoms and subatomic particles. What they discovered was shocking. At the smallest scales, reality operates nothing like our everyday experience. Particles exist in multiple states simultaneously until observed. They can tunnel through barriers that should be impossible to cross. They can be entangled across vast distances, instantly affecting each other in ways that Einstein famously called spooky action at a distance. Quantum mechanics has given us lasers, computers, medical imaging, and countless other technologies. It's arguably the most successful theory in the history of science, predicting experimental results with breathtaking precision. But here's where things get complicated. Quantum mechanics describes three of the four fundamental forces beautifully: the electromagnetic force, which governs light and electricity; the weak nuclear force, responsible for certain types of radioactive decay; the strong nuclear force, which holds atomic nuclei together. All three play by quantum rules. But gravity is the rebel. It refuses to fit into the quantum framework. When physicists try to apply quantum mechanics to gravity, their equations explode into infinities. Mathematical nonsense replaces sensible predictions. It's as if gravity speaks a completely different language from the other forces. This creates one of the most profound puzzles in modern physics. On one side, we have general relativity, which describes gravity as smooth, continuous curves in space-time. It works magnificently for large objects like planets, stars, and galaxies. On the other side, we have quantum mechanics, which describes everything else in terms of discrete packets of energy and probability waves. It excels at explaining atoms, molecules, and subatomic particles. The problem becomes critical when we try to understand extreme situations where both theories should apply. What happens inside a black hole where gravity becomes so intense that space-time itself might break down into quantum foam? How did the universe begin? when all matter and energy were compressed into a space smaller than an atom? What occurs when gravitational fields become so strong that quantum effects can no longer be ignored? These questions point to a fundamental incompleteness in our understanding. It's like having two different maps of the same territory that don't align at the borders. One map works perfectly for cities and highways, the other for wilderness and mountains. But where they should connect, there's only blank space. Einstein himself recognized this problem and spent the last 30 years of his life searching for a unified field theory that could merge gravity with electromagnetism. He never succeeded, but his dream lives on in the minds of physicists today. They call it the theory of everything, or sometimes more modestly, quantum gravity. The stakes couldn't be higher. A successful unification wouldn't just solve a mathematical puzzle, it would reveal the deepest secrets of reality itself. How did the universe begin? What lies beyond the event horizon of a black hole? Are there other dimensions of space and time that we can't perceive? Could we manipulate gravity the way we manipulate electromagnetic fields? But the challenge is immense. Light speed and gravity seem to operate by fundamentally different rules. Light speed is absolute, the same for all observers no matter how they're moving. Gravity is relative, bending space and time in ways that depend on your perspective. Quantum mechanics is probabilistic, describing what might happen. General relativity is deterministic, predicting exactly what will occur. Yet there are tantalizing hints that these seemingly incompatible pillars might share a common foundation. Both light and gravitational waves travel at exactly the same speed through empty space. Both are affected by the curvature of space-time. Both play crucial roles in the most extreme environments in the universe, from the surface of neutron stars to the edge of black holes. The story of modern physics is the story of unification. Maxwell unified electricity and magnetism into electromagnetism. Einstein unified space and time into space-time. Physicists later unified electromagnetism with the weak nuclear force into the electroweak interaction. Each unification revealed deeper truths about nature and opened new technological possibilities. Today's physicists believe that the next great unification, the marriage of light speed and gravity, will be the most profound yet. It promises to complete Einstein's vision and give us the final theory that explains everything from the smallest quantum fluctuations to the largest cosmic structures. But this unification requires us to think in radically new ways. We might need to abandon some of our most cherished assumptions about space, time, and reality itself. We might discover that what we call particles are actually vibrating strings in 11 dimensions. We might learn that space and time are not fundamental, but emerge from something even more basic. We might find that gravity itself is an illusion, a byproduct of deeper quantum processes. The journey toward this ultimate theory is far from over. In fact, we may be standing at the beginning of the most exciting chapter in the history of physics. The tools we need, from powerful particle accelerators to space-based gravitational wave detectors, are finally becoming available. The theoretical frameworks, from string theory to loop quantum gravity, are becoming more sophisticated. The cracks in our current foundation aren't signs of failure. They're invitations to dig deeper, to question everything we think we know, and to prepare for discoveries that will transform our understanding of existence itself. The universe is waiting to reveal its deepest secrets, and the key may lie in understanding how light speed and gravity are two aspects of a single, magnificent reality. The two pillars of modern physics have served us well, but their cracks demand that we build something new, something that can unite the quantum world of the very small with the relativistic world of the very large. The quest for this unification isn't just an academic exercise, it's humanity's attempt to read the mind of the cosmos itself. Imagine you're a detective in the 1860s, and you've just stumbled upon the crime of the century. The evidence is scattered across a series of elegant equations, each one a clue pointing to something extraordinary hidden in the fabric of reality itself. The detective's name was James Clerk Maxwell, and what he discovered would forever change our understanding of light, electricity, and the very nature of space and time. Maxwell wasn't looking for the speed of light when he began his investigation. He was trying to solve a completely different mystery, figuring out how electricity and magnetism worked together. Scientists had known for decades that these two phenomena were somehow connected. Move a magnet near a coil of wire and electricity flows. Send electricity through a wire and it creates a magnetic field. But nobody understood why. Maxwell approached this puzzle like a master architect, building mathematical structures that could house both electric and magnetic phenomena under one roof. What emerged from his work were 4 equations, now called Maxwell's equations, that described how electric and magnetic fields dance together through space and time. But here's where the story takes a stunning turn. When Maxwell combined his equations and solved them, something unexpected fell out of the mathematics. The equations predicted that electric and magnetic fields could create waves that propagated through empty space at a very specific speed. When Maxwell calculated this speed, he got a number that made his heart race, approximately 300 million meters per second. That number was already famous. It was the speed of light, measured by previous experiments. In that moment, Maxwell realized something profound. Light wasn't some mysterious substance flowing through space. Light was an electromagnetic wave, a rippling disturbance in electric and magnetic fields that traveled at exactly the speed his equations predicted. This revelation was like discovering that 2 seemingly different languages were actually dialects of the same tongue. Light, electricity, and magnetism were all aspects of a single electromagnetic phenomenon. Radio waves, X-rays, infrared radiation, visible light, they were all electromagnetic waves differing only in their frequency and wavelength. But Maxwell's discovery raised a perplexing question that would haunt physics for the next 40 years. If light was a wave, what was it waving through? Ocean waves move through water, sound waves move through air, but what medium carried electromagnetic waves through the vacuum of space? Scientists invented an answer. The luminiferous ether, an invisible substance that supposedly filled all of space and provided the medium for light waves. They imagined this ether as perfectly transparent, completely massless, yet rigid enough to transmit waves at enormous speed. Earth was thought to move through this ether like a ship cutting through an cosmic ocean. The problem was that nobody could detect this ether. In 1887, Albert Michelson and Edward Morley designed an ingenious experiment to measure Earth's motion through the ether. They reasoned that if Earth was moving through this medium, light should travel slightly faster in some directions than others, just as a swimmer moves faster with the current than against it. The Michelson-Morley experiment was a masterpiece of precision. They used an interferometer, a device that splits a beam of light, sends the parts along different paths, then recombines them. If Earth was moving through the ether, the recombined light beams should create a distinctive interference pattern as the planet's motion affected the light's travel time. The result was shocking. No matter how they oriented their apparatus, no matter what time of year they performed the experiment, they detected absolutely no motion through the ether. The speed of light was exactly the same in all directions. It was as if the universe was conspiring to hide Earth's motion through this mysterious medium. For 18 years, this null result puzzled the greatest minds in physics. Some proposed that the ether dragged along with Earth. Others suggested that objects contracted in the direction of their motion through the ether. These explanations grew increasingly convoluted and unsatisfying. Then came Albert Einstein with a solution so radical it seemed almost absurd. What if there was no ether at all? What if the speed of light in vacuum was simply a fundamental constant of nature, the same for all observers regardless of their motion? What if Maxwell's equations were telling us something much deeper about the structure of reality itself? Einstein's insight led to special relativity, published in 1905. The theory rested on two simple postulates that revolutionized physics. First, the laws of physics are the same in all inertial reference frames. Second, the speed of light in vacuum is the same for all observers, regardless of their motion or the motion of the light source. These might seem like innocent assumptions, but their consequences are mind-bending. If the speed of light is constant for everyone, then space and time themselves must be relative. When you move at high speeds, time slows down, distances contract, and events that appear simultaneous to you might occur at different times for someone else. Consider a simple thought experiment. You're standing on a train platform watching a train rush past at 90% the speed of light. A passenger on the train shines a flashlight forward. From the passenger's perspective, the light beam travels away at exactly 300 million meters per second. Classical physics would say that from your perspective on the platform, the light should be moving at the train's speed plus the light speed, nearly twice the speed of light. But Einstein's relativity says no. You on the platform also measure the light beam, traveling at exactly 300 million meters per second. The universe accomplishes this seemingly impossible feat by adjusting space and time themselves. The passengers' clocks run slower than yours, their measuring rods are contracted, and their definition of simultaneity differs from yours. This isn't just theoretical speculation. Every GPS satellite orbiting Earth experiences these relativistic effects. Their clocks run slightly faster than clocks on Earth's surface because they're in a weaker gravitational field and moving at high speed relative to the ground. Without corrections for these time dilations, GPS would accumulate errors of several kilometers per day. The constancy of light speed also explains why nothing with mass can reach or exceed this cosmic speed limit. As an object accelerates, its energy increases, but instead of just making it go faster forever, that energy begins to increase the object's relativistic mass. The closer you get to light speed, the more energy is required for each additional increment of velocity. To actually reach light speed would require infinite energy, which is impossible. Photons, the particles of light, can travel at light speed precisely because they have no mass. They exist in a strange state where they can only move at this one speed. A photon can never be at rest, never slow down, never speed up. From the moment of its creation to its absorption, it travels at exactly 300 million meters per second. This creates a bizarre perspective problem. From our point of view, a photon emitted by a distant star takes millions of years to reach us. But from the photon's perspective, if it could have one, the journey is instantaneous. Time dilation at light speed becomes so extreme that no time passes at all for the photon. It experiences its entire existence as a single moment, connecting its emission and absorption into one eternal now. The special nature of light speed extends beyond just electromagnetic radiation. Einstein's famous equation, E equals mc squared, reveals that this speed is embedded in the very relationship between matter and energy. Every particle, every atom, every object contains enormous amounts of energy locked away in its mass, and the conversion factor is the speed of light squared. This means that light speed isn't just the speed of light, it's the speed of causality itself. Information cannot travel faster than light speed, because that would allow effects to precede their causes, creating paradoxes that would tear apart the logical structure of the universe. When you wiggle your finger, the electromagnetic fields around it can't instantly adjust everywhere in space. The change propagates outward at light speed, maintaining the cosmic order of cause and effect. But here's where things get even more interesting. Light speed also appears in contexts that seem to have nothing to do with light. Gravitational waves, ripples in space-time itself, also travel at exactly light speed. This suggests a deeper connection between electromagnetic phenomena and the geometry of space-time. The constancy of light speed also led Einstein to realize that space and time aren't separate entities, but form a unified, four-dimensional space-time continuum. Events aren't just located in space, they're located in space-time, with a specific position along the time dimension as well as the three spatial dimensions. This space-time has a peculiar geometry where the shortest path between two events isn't necessarily a straight line in space, but follows what physicists call a geodesic in space-time. These geodesics respect the fundamental role of light speed in defining the causal structure of reality. Light speed also determines how we can slice space-time into space and time. Different observers moving at different velocities will disagree about what events happen at the same time and what the distances are between objects. But they'll all agree about space-time intervals, quantities that combine spatial and temporal separations in a way that remains constant for all observers. The more we study light speed, the more central it becomes to our understanding of reality. It's not just a speed limit, it's a conversion factor between space and time, between matter and energy, between cause and effect. It's woven so deeply into the fabric of physics that changing its value would fundamentally alter the nature of existence itself. Yet despite its fundamental importance, light speed raises as many questions as it answers. Why does it have the specific value it does? Is it truly constant throughout the universe and across all time? Could there be phenomena that somehow circumvent this cosmic speed limit without violating causality? These questions become even more intriguing when we consider gravity. Unlike electromagnetic fields, gravitational effects also propagate at light speed, but gravity seems to operate by completely different rules. While light follows straight paths through curved space-time, gravity is the curvature itself. This suggests that light speed and gravity might be connected at an even deeper level than we currently understand. The story of light speed is far from over. As we probe deeper into the quantum realm and explore the most extreme gravitational environments in the universe, we continue to discover new aspects of this fundamental constant. Each discovery reveals more about why the universe chose this particular speed as its ultimate limit, and how this choice shaped everything from atoms to galaxies. Light speed stands as one of nature's most profound revelations, a cosmic constant that bridges the gap between the mundane and the magnificent, between the quantum and the cosmic. But as we'll see, when gravity enters the picture, even this fundamental constant begins to reveal new layers of mystery and wonder. Close your eyes and imagine you're floating in the most perfect darkness, suspended in the void of space, with nothing but your thoughts and the gentle pull you feel toward a massive star nearby. Now here's the question that will change everything. Are you falling toward that star because it's pulling you with some invisible force? Or are you simply following the straightest possible path through a reality that has been fundamentally warped by the star's presence? For over 2 centuries, humanity lived with Isaac Newton's answer to this question. Gravity was a force, mysterious and instantaneous, reaching across the cosmos to pull objects together. Newton's law of universal gravitation worked beautifully, predicting the orbits of planets, the paths of comets, and the motion of projectiles here on Earth. It was so successful that it seemed to reveal gravity's true nature, a fundamental force that acted at a distance. But Newton himself was troubled by this explanation. How could objects separated by millions of kilometers instantly know about each other's presence? How could the sun reach across empty space to grab Earth and keep it in orbit? Newton famously wrote that he would not feign hypotheses about gravity's mechanism. He could describe what it did, but not what it was. Einstein refused to accept this mystery. In 1907, while working as a patent clerk in Bern, he had what he later called his happiest thought. He imagined a person falling freely in a gravitational field and realized that such a person would feel completely weightless. More importantly, they wouldn't be able to tell the difference between floating in empty space far from any massive objects and falling freely in a gravitational field. This insight led Einstein to a revolutionary idea. What we experience as gravity might not be a force at all, but rather a consequence of the geometry of space-time itself. Massive objects don't pull on other objects. They warp the fabric of space and time, and we experience this warping as gravity. To understand this concept, imagine space-time as a vast trampoline stretched tight and flat. Now place a bowling ball in the center. The ball creates a depression, curving the trampoline's surface. If you roll marbles nearby, they'll naturally curve toward the bowling ball, following the contours of the warped surface. They're not being pulled by a mysterious force. They're simply following the straightest path available in the curved geometry. This is exactly how Einstein reimagined gravity in his general theory of relativity, published in 1915. Massive objects curve space-time, and other objects follow geodesics, the straightest possible paths through this curved geometry. What we perceive as gravitational attraction is actually objects moving along the natural contours of warped space-time. The implications of this geometric view of gravity are staggering. Space and time aren't just the stage on which physics plays out. They're active participants in the cosmic drama. They can stretch, compress, twist, and ripple like a cosmic ocean responding to the matter and energy within it. Einstein's equations, 10 interconnected differential equations of fearsome complexity, describe precisely how matter and energy curve space-time and how this curvature guides the motion of matter and energy in return. It's a beautiful cosmic feedback loop where geometry determines motion and motion reshapes geometry. But here's where the story takes a fascinating turn. If space-time is curved by massive objects, then light, despite having no mass, should also follow these curves. Light always travels in straight lines through space, but in curved space-time, straight lines are themselves curved. This prediction led to one of the most dramatic confirmations in the history of science. During a total solar eclipse in 1919, Arthur Eddington measured the positions of stars whose light passed close to the sun. Einstein's theory predicted that the sun's gravity should bend this starlight, making the stars appear slightly displaced from their normal positions. When Eddington's measurements confirmed this prediction exactly, Einstein became an international celebrity overnight. Today we call this phenomenon gravitational lensing, and it's become one of astronomy's most powerful tools. When light from distant galaxies passes near massive objects like galaxy clusters, it gets bent and focused like light through a lens. Sometimes this creates multiple images of the same distant galaxy, or stretches it into beautiful arcs across the sky. Gravitational lensing has allowed us to study galaxies so distant that their light has traveled for over 13 billion years to reach us. But gravitational lensing reveals something profound about the relationship between light and gravity. Light has no mass, yet it responds to gravitational fields. How can this be? The answer lies in understanding that gravity doesn't pull on mass, it curves space-time itself. Light follows geodesics through space-time, just like massive objects do, because geodesics are simply the straightest paths available in whatever geometry exists. This creates a beautiful symmetry. Light defines the causal structure of space-time through its constant speed, while gravity defines the geometric structure of space-time through its curvature. These aren't separate phenomena acting independently. They're two aspects of space-time's unified nature. Consider what happens near a black hole, nature's most extreme gravitational environment. As you approach the event horizon, space-time becomes so severely curved that even light cannot escape. But from the perspective of general relativity, light near a black hole is still traveling in straight lines. It's just that space-time itself is so warped that all straight paths lead back toward the black hole's center. The event horizon represents a point of no return, not because some force overcomes light, but because the geometry of space-time itself becomes so curved that all future directed paths point inward. It's like being on a mountainside so steep that every step you take, no matter which direction you try to go, leads further downhill. Inside the black hole, the curvature becomes so extreme that space and time exchange roles. The radial direction toward the center becomes time-like, meaning that falling toward the singularity becomes as inevitable as moving forward through time. Meanwhile, what we normally think of as time becomes space-like, allowing for the possibility of closed time-like curves and other exotic space-time geometries. Black holes also reveal another fascinating connection between light and gravity. The surface area of a black hole's event horizon is directly proportional to its entropy, the amount of information it contains. This suggests that information can be encoded on the two-dimensional surface of the event horizon, even though the black hole exists in three-dimensional space. This holographic principle hints at deep connections between gravity, information, and the fundamental nature of space-time itself. Gravitational time dilation provides another window into how gravity bends reality. Clocks run slower in stronger gravitational fields, an effect that's been precisely measured using atomic clocks at different altitudes on Earth. This isn't just a curious side effect, it's a fundamental consequence of space-time curvature. From the perspective of someone far from a gravitational source, time appears to slow down near massive objects. Light emitted from strong gravitational fields appears redshifted, stretched to longer wavelengths as it climbs out of the gravitational well. This gravitational redshift has been observed in light from white dwarf stars and neutron stars, providing another confirmation of Einstein's geometric vision of gravity. But perhaps the most remarkable discovery about gravity's relationship with light came in 2015 with the first detection of gravitational waves by the Laser Interferometer Gravitational Wave Observatory, or LIGO. These ripples in space-time itself, predicted by Einstein a century earlier, travel at exactly the speed of light. Gravitational waves are produced when massive objects accelerate asymmetrically, like two black holes spiraling into each other. These cosmic collisions create ripples that propagate outward through space-time at light speed, alternately stretching and compressing space as they pass. LIGO detects these waves by measuring incredibly tiny changes in the length of laser beams traveling between mirrors separated by several kilometers. The fact that gravitational waves travel at light speed reveals a profound connection between gravity and electromagnetism. Both are manifestations of space-time's geometry, and both respect the cosmic speed limit that light speed imposes on the propagation of information and causality. This connection becomes even more intriguing when we consider that both light and gravitational waves can carry energy and momentum. When gravitational waves pass through space, they carry away energy from their source, causing inspiraling black holes to gradually lose orbital energy and spiral closer together. Similarly, light carries electromagnetic energy and can exert radiation pressure on objects it encounters. The energy-carrying capacity of both light and gravitational waves suggests that they're not just passive phenomena moving through space-time, but active participants in the cosmic energy budget. They can do work, transfer information, and influence the evolution of the systems that produce them. Yet, despite these similarities, light and gravity seem to operate by fundamentally different mechanisms. Electromagnetic fields are described by Maxwell's equations, which treat space and time as a fixed background stage. Gravitational fields are described by Einstein's equations, which treats space-time as a dynamic, evolving entity that participates actively in gravitational phenomena. This difference becomes crucial when we try to understand extreme environments where both effects are important. Near the surface of a neutron star, electromagnetic fields can become so strong that they affect space-time curvature, while gravitational fields can become so intense that they influence electromagnetic phenomena. The interplay between these effects creates some of the most complex and beautiful phenomena in the universe. Neutron stars, with magnetic fields trillions of times stronger than Earth's and gravitational fields billions of times more intense, serve as natural laboratories for studying the interaction between light and gravity. The light emitted by these objects is twisted and focused by their intense gravitational fields, creating lighthouse-like beams that sweep across space as the stars rotate. Some neutron stars, called magnetars, have magnetic fields so strong that they warp the quantum vacuum itself, creating a medium through which light travels differently depending on its polarization. This quantum effect, predicted by theory but observed only recently, shows how extreme gravity can influence even the fundamental properties of empty space. The study of black holes has revealed even more exotic connections between light and gravity. The information paradox asks what happens to information that falls into a black hole. Does it disappear forever, violating quantum mechanics' requirement that information be conserved? Or does it somehow escape, perhaps encoded in the Hawking radiation that theoretical calculations suggest black holes should emit? Hawking radiation itself represents a fascinating merger of quantum mechanics, thermodynamics, and gravity. The intense gravitational fields near black holes can create particle pairs from the quantum vacuum, with one particle falling into the black hole, while the other escapes as radiation. This process suggests that black holes aren't perfectly black, but gradually evaporate by emitting light and other particles. The temperature of this radiation is inversely proportional to the black hole's mass, meaning that smaller black holes are actually hotter than larger ones. For stellar mass black holes, this radiation is far too faint to detect with current technology, but it represents a fundamental connection between gravity, quantum mechanics, and thermodynamics. As we probe deeper into the relationship between light and gravity, we discover that they're not just two phenomena that happen to coexist in the universe. They're intimately connected aspects of space-time's fundamental nature. Light reveals the causal structure of space-time through its role in defining simultaneity and the flow of information. Gravity reveals the geometric structure of space-time through its curvature of the cosmic stage itself. But this beautiful geometric picture raises profound questions. If gravity is just geometry, why does it seem so different from the other forces? Why can't we reconcile general relativity's smooth, continuous space-time with quantum mechanics' discrete, probabilistic description of reality? The answers to these questions may require us to rethink the very nature of space, time, and the forces that govern them. The universe has revealed that gravity doesn't pull, it warps. Light doesn't just illuminate, it defines the very structure of causality and information flow. Together, they create a cosmic symphony where geometry and light dance together across the vast stage of space-time. But the full score of this symphony remains tantalizingly beyond our current understanding. Imagine trying to describe the ocean using two completely different languages. In one language, you speak of smooth flowing currents and gentle waves that roll continuously across vast distances. In the other language, you can only talk about discrete droplets, individual molecules bouncing chaotically against each other in sudden, unpredictable jumps. Both descriptions capture something true about water, but when you try to translate between them, meaning gets lost and contradictions emerge. This is precisely the situation physics finds itself in. when trying to describe the universe at its most fundamental level. General relativity speaks the language of smooth, continuous spacetime, flowing and curving like a cosmic ocean. Quantum mechanics speaks the language of discrete packets, sudden jumps, and fundamental uncertainty. Both languages work magnificently in their own domains. But when we try to apply them simultaneously to the same phenomena, the universe seems to speak in contradictory tongues. The quantum world operates by rules that would seem absurd in our everyday experience. Energy comes in discrete packets called quanta. Particles can exist in multiple states simultaneously until observed. Empty space itself seethes with virtual particles popping into and out of existence. Position and momentum cannot be known simultaneously with perfect precision. The act of observation fundamentally changes what is being observed. These quantum principles have given us lasers, transistors, magnetic resonance imaging, and quantum computers. They describe the behavior of atoms, molecules, and subatomic particles with breathtaking accuracy. When physicists calculate the magnetic moment of an electron using quantum electrodynamics, they get agreement with experiment to 12 decimal places. It's like predicting the distance from New York to Los Angeles, to within the width of a human hair. But gravity refuses to play by quantum rules. When physicists try to apply quantum mechanics to Einstein's curved spacetime, the mathematics explodes into infinities that have no physical meaning. The smooth geometry of general relativity and the grainy uncertainty of quantum mechanics seem fundamentally incompatible. To understand why this incompatibility is so profound, consider what happens when we try to measure the curvature of spacetime at very small scales. According to quantum mechanics, there's a fundamental limit to how precisely we can measure anything. The more precisely we try to pin down the geometry of a small region of spacetime, the more energy we need to concentrate in that region. But energy curves spacetime, so our very attempt to measure the geometry changes the geometry we're trying to measure. At the smallest scales, called the Planck scale, this effect becomes overwhelming. The Planck length is about 10 to the minus 35 meters, so small that if you enlarged an atom to the size of the observable universe, the Planck length would still be smaller than a tree. At this scale, quantum fluctuations in the energy density become so large that they should create a foaming, chaotic spacetime where the smooth geometry of general relativity breaks down completely. This quantum foam represents one of the deepest mysteries in physics. At scales larger than the Planck length, spacetime appears smooth and well-behaved, following Einstein's equations precisely. But if quantum mechanics is correct, this smoothness should be an illusion, hiding an underlying reality that fluctuates wildly on the smallest scales. The problem becomes even more acute when we consider black holes. According to general relativity, matter falling into a black hole gets compressed to infinite density at the singularity, creating infinite curvature in space-time. But infinity is not a number that appears in any sensible physical theory. It's a sign that our equations have broken down and are no longer giving us meaningful answers. Quantum mechanics suggests that something must happen before we reach these infinities. Perhaps space-time itself breaks down into discrete units at the Planck scale. Perhaps new physical processes kick in that prevent the formation of true singularities. But without a quantum theory of gravity, we have no way to calculate what actually happens in these extreme conditions. The incompatibility goes deeper than just mathematical difficulties. General relativity is a deterministic theory. Given the initial conditions and the distribution of matter and energy, Einstein's equations tell you exactly how space-time will evolve. There's no randomness, no uncertainty, just the inexorable unfolding of geometric destiny. Quantum mechanics, by contrast, is fundamentally probabilistic, you can calculate the probability that a particle will be found in a particular location or state, but you cannot predict with certainty what will happen in any individual measurement. The universe, at its most basic level, appears to run on chance rather than clockwork. These contrasting philosophies create paradoxes when applied together. Consider Hawking radiation, the theoretical process by which black holes slowly evaporate by emitting particles. The calculation of this effect requires both quantum mechanics to describe particle creation near the event horizon and general relativity to describe the black hole's space-time geometry. But the resulting predictions lead to the information paradox. If black holes evaporate completely, what happens to the information that fell into them? According to quantum mechanics, information cannot be destroyed. Every quantum process must be reversible in principle, even if the reversal is practically impossible. But if information disappears into an evaporating black hole, this fundamental principle appears to be violated. The paradox has sparked decades of debate and led to proposals ranging from firewalls at event horizons to the holographic principle that suggests reality might be fundamentally two-dimensional. Another manifestation of the quantum gravity problem appears in cosmology. According to the Big Bang model, the universe began in a state of infinite density and temperature called the initial singularity. But just as with black hole singularities, infinity signals the breakdown of our physical theories. To understand what really happened in the first moments after the Big Bang, we need a quantum theory of gravity. The period called cosmic inflation, when the universe expanded exponentially in the first fraction of a second, might have been driven by quantum effects in the gravitational field. Tiny quantum fluctuations in the early universe's density could have been stretched by inflation to become the seeds of galaxies and galaxy clusters we see today. But calculating these effects precisely requires understanding how quantum mechanics and gravity work together. The search for quantum gravity has revealed fundamental questions about the nature of space and time themselves. In quantum field theory, empty space is not actually empty, but filled with quantum fields that fluctuate constantly. These fluctuations have measurable effects, like the Casimir force between closely spaced metal plates. But if space-time itself is subject to quantum fluctuations, what does this mean for our concepts of distance, duration, and causality? Some approaches to quantum gravity suggest that space and time might not be fundamental, but emergent properties that arise from some deeper, more basic reality. Just as temperature emerges from the average motion of molecules, space-time might emerge from the interactions of more fundamental entities that exist below the Planck scale. This possibility challenges our most basic assumptions about reality. We experience space as a smooth continuum that extends in 3 dimensions, and time as a flowing parameter that moves steadily from past to future. But these experiences might be illusions created by our limited perspective, like thinking the Earth is flat because we can only see a small portion of its curved surface. The problem of unifying quantum mechanics and gravity also reveals deep questions about the nature of measurement and observation. In quantum mechanics, the act of measurement causes the quantum wave function to collapse, transforming a superposition of possible states into a single definite outcome. But what constitutes a measurement? How does this process work when gravity is involved? If space-time itself is quantized, then the process of measurement might involve the geometry of space-time in fundamental ways. The apparatus used to make a measurement occupies space and has gravitational effects, however small. In principle, these effects should be included in any complete quantum description of the measurement process. This leads to mind-bending scenarios where the act of measuring a quantum system might alter the curvature of space-time in ways that affect the measurement itself. The boundary between the quantum system being measured and the classical measuring apparatus becomes blurred when gravity is taken into account. The incompatibility between quantum mechanics and general relativity also shows up in high-energy particle physics. When particles collide at very high energies, they can create new particles and even possibly microscopic black holes. At these energies, the quantum nature of matter and the gravitational effects of concentrated energy should both be important, but we have no consistent theory to describe such processes. Particle accelerators like the Large Hadron Collider can reach energies that are enormous by everyday standards, but still far below the Planck energy where quantum gravitational effects become strong. To probe quantum gravity directly through particle physics would require accelerators larger than the solar system, clearly beyond any conceivable technology. This experimental inaccessibility makes quantum gravity one of the most challenging problems in physics. Unlike other areas where theory and experiment can guide each other, quantum gravity theorists must rely primarily on mathematical consistency and conceptual elegance to guide their search for the correct theory. The mathematical difficulties of combining quantum mechanics and gravity stem from the different ways the two theories treat space and time. In quantum field theory, space and time provide a fixed background stage on which quantum fields perform their probabilistic dance. In general relativity, space-time is a dynamic player that responds to and influences the matter and energy within it. When you try to quantize gravity using the same methods that work for other forces, you get equations with infinite terms that cannot be removed by any known mathematical technique. These infinities arise because gravitational interactions become stronger at higher energies, unlike electromagnetic interactions, which become weaker. This makes gravity non-renormalizable in the technical language of quantum field theory. The failure of standard quantization techniques has led physicists to explore radically different approaches. String theory replaces point particles with vibrating strings in 10 or 11 dimensions. Loop quantum gravity attempts to quantize space-time itself, creating a granular structure at the Planck scale. Causal dynamical triangulation builds space-time from discrete building blocks. Each approach offers different insights, but none has yet provided a complete, experimentally tested theory of quantum gravity. The quantum gravity problem also intersects with deep questions about the nature of time. In general relativity, time is just another coordinate, and there's no universal notion of simultaneity. Different observers disagree about what events happen at the same time. But quantum mechanics seems to require a universal time parameter to describe the evolution of quantum states. This tension between the relativistic and quantum pictures of time has led some physicists to propose that time itself might be an emergent property rather than a fundamental feature of reality. Perhaps the universe is fundamentally timeless, and what we experience as the passage of time arises from the way quantum information becomes entangled and spreads throughout space. The quest to resolve the quantum gravity problem continues to push physics toward ever more exotic ideas. Some theories propose that reality has a holographic structure where all the information in a volume of space is encoded on its boundary. Others suggest that space-time might be a quantum error-correcting code, naturally protecting information from the destructive effects of quantum decoherence. As we stand at the boundary between the quantum and gravitational realms, we find ourselves confronting the deepest questions about the nature of reality itself. The smooth space-time of general relativity and the discrete quanta of quantum mechanics represent two of humanity's greatest intellectual achievements. But their incompatibility suggests that our understanding of the universe remains fundamentally incomplete. The resolution of this incompatibility promises to reveal new truths about space, time, matter, energy, and the very foundations of existence itself. Picture a brilliant mind in his Princeton study, surrounded by blackboards covered in equations that grow more complex with each passing day. The year is 1950, and Albert Einstein, now 71 years old, has spent the last 3 decades of his life chasing a dream that many of his colleagues consider impossible. While younger physicists celebrate the triumphs of quantum mechanics, Einstein remains convinced that the universe must have a deeper, more elegant structure where all forces emerge from a single, beautiful mathematical framework. Einstein's quest for a unified field theory began almost immediately after he completed general relativity. He had shown that gravity could be understood as the curvature of spacetime itself, and this geometric insight tantalized him with the possibility that other forces might have similar geometric origins. If gravity was the warping of spacetime, perhaps electromagnetism could be understood as some other type of geometric feature, like the twisting or rotation of additional dimensions. This wasn't merely an academic exercise for Einstein. He believed deeply that nature must be comprehensible, that beneath the apparent complexity of physical phenomena lay simple, elegant principles waiting to be discovered. The idea that the universe operated according to multiple, unrelated sets of rules offended his sense of cosmic harmony. There had to be a theory of everything, a single equation that could encompass all of physics. Einstein's first attempts at unification focused on combining gravity with electromagnetism, the only 2 forces known at the time. He explored various mathematical approaches, trying to extend his geometric description of gravity to include electromagnetic fields. Some of his attempts involved adding extra dimensions to spacetime. Others tried to incorporate electromagnetic potentials directly into the metric tensor that describes spacetime curvature. One of his most promising approaches was based on the work of Theodor Kaluza and Oskar Klein, who had proposed in the 1920s that the universe might actually have 5 dimensions instead of the 4 we experience. In their theory, the 5th dimension was curled up so tightly that it was invisible at normal scales, but its geometry could give rise to electromagnetic forces. The Kaluza-Klein theory was mathematically elegant and provided a tantalizing glimpse of how unification might work. By moving through the 5th dimension, particles could appear to gain or lose electric charge from the perspective of our 4-dimensional world. The theory naturally explained why electric charge was quantized and why it was conserved in all interactions. But the Kaluza-Klein theory also had problems. It predicted the existence of a new scalar field that had never been observed, and it couldn't explain why the 5th dimension should be curled up in the first place. More fundamentally, it was developed before the discovery of the strong and weak nuclear forces, so it was attempting to unify only half of the forces that actually exist in nature. Einstein continued his unification efforts, even as physics moved in different directions. The 1920s and 30s saw the development of quantum mechanics, which proved incredibly successful at describing atomic and molecular phenomena. Young physicists like Werner Heisenberg, Erwin Schrödinger, and Paul Dirac were making breakthrough after breakthrough, revolutionizing our understanding of matter and energy. But Einstein remained skeptical of quantum mechanics' probabilistic nature. His famous declaration that God does not play dice reflected his belief that the apparent randomness of quantum phenomena must be hiding some deeper deterministic reality. He hoped that a unified field theory would reveal this hidden reality and restore determinism to physics. Throughout the 1930s and 40s, Einstein published a series of papers exploring different approaches to unification. He investigated theories based on distant parallelism, where spacetime had both curvature and torsion. He explored approaches that used complex numbers instead of real numbers to describe geometric relationships. He even considered theories where the fundamental equations were not differential equations, but finite difference equations. None of these approaches ultimately succeeded, but they established important principles that continue to guide unification efforts today. Einstein realized that any successful unified theory would need to be geometrical in nature. Extending his insights about gravity to to encompass all forces. He also understood that unification might require radical changes to our concepts of space and time themselves. While Einstein worked largely alone on his unification quest, other physicists began developing what would become known as gauge theories. These theories showed how forces could arise from requirements that the laws of physics remain unchanged under certain transformations. The electromagnetic force, for example, could be understood as arising from the requirement that physics be invariant under changes in the phase of quantum wave functions. Hermann Weyl, one of the pioneers of gauge theory, initially proposed that electromagnetic forces arose from requirements that physics be invariant under changes in the scale or gauge of measurement. Although his original proposal was flawed, it introduced the crucial idea that forces could be understood as consequences of symmetry requirements rather than as fundamental entities in their own right. The gauge theory approach proved remarkably successful when applied to the other forces of nature. In the 1950s and 60s, physicists developed gauge theories for the weak nuclear force, which governs certain types of radioactive decay, and the strong nuclear force, which holds atomic nuclei together. These theories showed that forces very different in strength and character could all be understood within the same conceptual framework. The real breakthrough came in the 1960s and 70s with the development of the Standard Model of particle physics. This theory successfully unified 3 of the 4 fundamental forces into a single mathematical framework based on gauge symmetry. The electromagnetic and weak forces were shown to be different aspects of a single electroweak force, while the strong force was described by a separate but related gauge theory. The Standard Model represented the greatest achievement in physics since general relativity. It explained the existence and properties of all known particles and forces, with the exception of gravity. Its predictions have been confirmed to extraordinary precision in thousands of experiments. The discovery of the Higgs boson in 2012 provided the final missing piece, confirming the mechanism by which particles acquire mass. But the Standard Model also revealed the magnitude of the unification challenge. The 3 forces it describes are unified only in a mathematical sense. At the energies we can access experimentally, they appear as distinct forces with very different strengths and properties. The electromagnetic force is about 100 times weaker than the strong force, while the weak force is much weaker still and operates only at very short distances. Physicists realized that these forces might become truly unified only at incredibly high energies, far beyond anything achievable in earthbound laboratories. At these energies, the apparent differences between the forces would disappear, revealing their common origin. This idea led to the development of Grand Unified Theories, or GUTS, which attempted to merge the 3 Standard Model forces into a single force. The simplest GUTS predicted that protons, the building blocks of atomic nuclei, should occasionally decay into lighter particles. Enormous underground detectors were built to search for this rare process, but after decades of observation, no proton decays have been detected. This doesn't definitively rule out grand unification, but it places severe constraints on the simplest models. GUTS also predicted the existence of magnetic monopoles, particles that carry isolated north or south magnetic poles. Despite extensive searches, no magnetic monopoles have been found, creating another puzzle for grand unification theories. Some models suggest that monopoles were produced in the early universe, but have since been diluted to undetectable levels by cosmic inflation. The quest for grand unification revealed deep connections between particle physics and cosmology. Many GUT models predicted that the universe should contain equal amounts of matter and antimatter, but observations show that matter dominates overwhelmingly. This matter-antimatter asymmetry might have been generated by rare processes in grand unified theories that violate certain symmetry principles. The unification program also highlighted the problem of hierarchy. Why is gravity so much weaker than the other forces? The gravitational attraction between two protons is about 10 to the 39th times weaker than their electromagnetic repulsion. This enormous hierarchy of force strengths remains one of the deepest mysteries in physics. Some physicists have proposed that gravity appears weak because it operates in extra dimensions that we cannot directly perceive. If gravity spreads out into additional spatial dimensions, while the other forces are confined to our three-dimensional space, it would naturally appear much weaker than it actually is. This idea has led to theories with large extra dimensions that might be detectable in high-energy particle experiments. The hierarchy problem becomes even more puzzling when you consider that quantum corrections should naturally drive all energy scales to either zero or the Planck scale, where quantum gravitational effects become important. The fact that the masses of elementary particles are much smaller than the Planck mass suggests that some mechanism must be protecting them from these quantum corrections. Supersymmetry, a hypothetical symmetry between particles of different quantum mechanical spin, was proposed as a solution to the hierarchy problem. Supersymmetric theories predict that every known particle has a heavier supersymmetric partner. These partner particles could cancel out the quantum corrections that would otherwise drive particle masses to enormous values. Supersymmetry also provides a natural candidate for dark matter, the mysterious substance that makes up most of the matter in the universe, but interacts only weakly with ordinary matter and light. The lightest supersymmetric particle would be stable and interact weakly with ordinary matter, exactly the properties expected for dark matter particles. Despite its theoretical appeal, supersymmetry has not been confirmed experimentally. The Large Hadron Collider has searched extensively for supersymmetric particles but found no evidence for them. This doesn't rule out supersymmetry completely, but it suggests that if supersymmetric particles exist, they are heavier than initially expected. The challenges facing grand unification and supersymmetry have led some physicists to explore even more radical approaches to unification. Some theories propose that all forces, including gravity, emerge from the dynamics of quantum information. Others suggest that space, time, and matter are all emergent properties of some more fundamental quantum mechanical system. The anthropic principle offers a different perspective on unification. This principle suggests that the apparent fine-tuning of physical constants might be explained by the existence of multiple universes with different physical laws. We observe the particular combination of forces and constants that we do, because only universes with these properties can support the formation of galaxies, stars, planets, and ultimately life. While the anthropic principle can explain why the universe appears fine-tuned for life, many physicists find it unsatisfying because it seems to give up on the goal of finding a unique, predictive theory. Instead of explaining why the universe has the properties it does, the anthropic principle suggests that all possible properties are realized somewhere in a vast multiverse. The search for unification has also been driven by aesthetic considerations. Physicists have long been guided by the belief that the fundamental laws of nature should be beautiful, elegant, and simple. This aesthetic sense has led to many important discoveries, from the symmetrical structure of Maxwell's equations to the geometric elegance of general relativity. But beauty can also be misleading. Nature might not care about human aesthetic preferences, and the most fundamental theory might turn out to be complex, ugly, or incomprehensible to human minds. The history of physics shows both examples where aesthetic considerations led to correct theories and cases where they led scientists astray. As we look back on more than a century of unification efforts, we see a pattern of partial successes and ultimate limitations. Each step forward has revealed new layers of complexity and raised new questions. The electromagnetic and weak forces have been unified, but only at energies far higher than those we normally encounter. grand unified theories remain unconfirmed by experiment. Gravity continues to resist incorporation into the quantum framework. Yet the dream of unification continues to inspire new generations of physicists. The mathematical tools and conceptual frameworks developed in pursuit of this dream have led to countless insights and technological applications. Even if complete unification remains elusive, the journey toward it has transformed our understanding of the universe. Einstein's quest for a unified field theory was ultimately unsuccessful, but his vision of a geometrical foundation for all physics has proven prophetic. Modern unified theories are indeed geometric, though they operate in abstract mathematical spaces rather than the familiar space-time of general relativity. The gauge symmetries that govern the standard model forces can be understood as geometric properties of these abstract spaces. The dream of unification also reflects something deep about human nature and our relationship with the cosmos. We seem driven to find patterns, to seek unity beneath diversity, to believe that the universe makes sense at its deepest level. Whether this drive will ultimately lead us to a theory of everything remains to be seen, but the search itself has already revealed wonders that would have seemed like magic to previous generations. As we stand on the threshold of new discoveries in particle physics, cosmology, and quantum gravity, Einstein's dream of unification remains as compelling as ever. The universe has shown us glimpses of its underlying unity through the success of gauge theories and the standard model. But the complete picture, the final theory that unifies light speed and gravity within a single framework, remains tantalizingly beyond our grasp, waiting for the next breakthrough that will revolutionize our understanding of reality itself. Imagine standing before two magnificent doors, each promising to reveal the deepest secrets of the universe. Behind the first door lies a reality where the fundamental building blocks of everything are not particles, but impossibly tiny, vibrating strings, dancing through dimensions we cannot see. Behind the second door awaits a universe where space and time themselves are not smooth and continuous, but built from discrete, quantum building blocks, smaller than anything we can measure. These are the two leading candidates for a theory of quantum gravity, and they could hardly be more different in their vision of reality's foundation. String theory emerged in the late 1960s from an unexpected source. Gabriele Veneziano, a young Italian physicist, was trying to understand the strong nuclear force when he stumbled upon a 200-year-old mathematical formula discovered by Leonhard Euler. This formula, originally developed for purely abstract mathematical reasons, seemed to describe the behavior of strongly interacting particles with remarkable accuracy. But there was something strange about Veneziano's discovery. The mathematics didn't describe particles as points, but as one-dimensional strings, vibrating and oscillating in ways that produce different particles depending on their vibrational patterns. It was as if the universe was a cosmic symphony, with each type of particle corresponding to a different note played on fundamental strings of energy. Initially, string theory was just an alternative approach to understanding the strong force. But as physicists explored its mathematical structure more deeply, they discovered something astonishing. The theory naturally included a massless particle with spin 2, exactly the properties that Einstein's theory attributed to the graviton, the hypothetical quantum particle that carries gravitational force. String theory wasn't just describing the strong force, it was predicting gravity. This unexpected emergence of gravity from string theory was like finding that your attempt to understand the rules of chess had accidentally solved the mystery of human consciousness. Nobody had been looking for quantum gravity in the mathematics of the strong force, but there it was, arising naturally from the requirement that the theory be mathematically consistent. The graviton that emerged from string theory behaved exactly as general relativity predicted, but it was embedded in a quantum mechanical framework that avoided the infinities that plagued other attempts to quantize gravity. The secret lay in the extended nature of strings themselves. Unlike point particles, which could get arbitrarily close to each other and create infinite forces, strings had a minimum size that smoothed out these dangerous interactions. But string theory came with a shocking requirement. For the mathematics to work consistently, space-time couldn't have the 4 dimensions we experience. Depending on the version of string theory, space needed to have either 9 or 10 dimensions, with time making the total either 10 or 11. Where were these extra dimensions hiding? The answer, string theorists proposed, lay in a process called compactification. Just as a garden hose appears one-dimensional from a distance, but reveals its circular cross-section when viewed up close, the extra dimensions might be curled up so tightly that they're invisible at the scales we can normally probe. Every point in our familiar 3-dimensional space might actually be a tiny 6 or 7-dimensional space, folded up in incredibly complex geometric patterns. These hidden dimensions weren't just mathematical abstractions. Their shape and size would determine the properties of particles and forces that we observe in our 3-dimensional world. Different ways of curling up the extra dimensions would produce different physics, potentially explaining why particles have the masses they do and why forces have their observed strengths. The geometry of these compact dimensions is described by some of the most beautiful mathematics ever discovered. Calabi-Yau manifolds, named after mathematicians Eugenio Calabi and Xingtung Yau, are 6-dimensional spaces with special geometric properties that preserve certain symmetries required by string theory. These manifolds have shapes so complex that they challenge our ability to visualize them, yet they might determine everything from the number of electron families to the strength of the weak nuclear force. String theory also predicted the existence of additional types of objects beyond just strings. D-branes, short for Dirichlet branes, are higher dimensional surfaces on which strings can end. These branes can have anywhere from 0 dimensions, making them points, to 9 dimensions, creating vast hypersurfaces that span most of space-time. Our entire observable universe might exist on a 3-dimensional brane, floating in a higher dimensional space. The brane world scenario offers elegant solutions to several puzzles in physics. Gravity might appear weak because it can spread out into all the extra dimensions, while the other forces are confined to our 3-dimensional brane. This could explain the hierarchy problem without requiring supersymmetry or other exotic mechanisms. But string theory's greatest strength is also its greatest weakness. The theory is so mathematically rich and flexible that it appears capable of describing almost any conceivable universe. Physicists have identified something like 10 to the 500 different ways to curl up the extra dimensions, each giving rise to different physical laws. This embarrassment of riches has been dubbed the landscape problem. Critics argue that a theory that can explain everything explains nothing. If string theory can accommodate any possible experimental result by choosing appropriate compactification, then it's not really making testable predictions. String theorists respond that the landscape might be a feature, not a bug, providing a natural explanation for the apparent fine-tuning of physical constants through the anthropic principle. Meanwhile, a completely different approach to quantum gravity was developing. Loop quantum gravity, pioneered by Carlo Rovelli, Lee Smolin, and Abhay Ashtekar, took Einstein's geometric vision of gravity seriously and attempted to quantize space-time itself, rather than treating it as a background for quantum fields. The central insight of loop quantum gravity is that space and time, when examined at the Planck scale, are not continuous, but made up of discrete, indivisible units. Just as matter is composed of atoms, space-time itself might be built from fundamental building blocks that cannot be subdivided further. In loop quantum gravity, these building blocks are described by quantum states that represent tiny loops and networks in space. The area of any surface and the volume of any region must come in discrete multiples of fundamental quantum units. space becomes a sort of fabric woven from quantum threads, with a granular structure that emerges only at the smallest scales. This granular picture of space-time has profound implications for black holes and cosmology. In classical general relativity, matter falling into a black hole gets compressed to infinite density at the singularity. But in loop quantum gravity, the discrete structure of space prevents infinite compression. Instead of a singularity, you get a quantum bounce that might connect our universe to another universe on the other side of the black hole. Similarly, the Big Bang singularity that appears in classical cosmology is replaced by a big bounce in loop quantum gravity. The universe might be cyclic, contracting to a minimum size determined by quantum geometry, then expanding again in an endless sequence of cosmic cycles. Our Big Bang might have been just the latest in an infinite series of cosmic rebounds. Loop quantum gravity makes specific, testable predictions about the granular structure of space-time. The discreteness of area and volume should leave subtle signatures in gravitational waves and the cosmic microwave background radiation. Future experiments might be sensitive enough to detect these quantum geometric effects, providing direct evidence for the theory. But loop quantum gravity also faces significant challenges. While it successfully quantizes general relativity, it has had much less success incorporating the other forces of nature. The standard model particles and forces seem to require a background spacetime to be properly defined, but loop quantum gravity eliminates this background in favor of dynamical quantum geometry. The contrast between string theory and loop quantum gravity reflects fundamentally different philosophies about the nature of reality. String theory embraces extra dimensions and exotic mathematical structures, viewing our familiar spacetime as an emergent approximation of a much richer underlying reality. Loop quantum gravity stays closer to Einstein's original vision, treating spacetime geometry as fundamental but subjecting it to quantum principles. String theory has deep connections to the holographic principle, the idea that all the information in a volume of space can be encoded on its boundary. This principle emerged from studies of black hole thermodynamics, where the entropy of a black hole was found to be proportional to the area of its event horizon rather than its volume. The AD-SCFT correspondence, discovered by Juan Maldacena, provides a concrete realization of holography in certain special spacetimes. In the AD-SCFT correspondence, a gravitational theory in a space with negative curvature, called anti-de Sitter space, is exactly equivalent to a quantum field theory without gravity living on the boundary of that space. This remarkable duality allows physicists to calculate properties of quantum gravity by solving easier problems in ordinary quantum field theory. The holographic principle suggests that our three-dimensional reality might itself be a holographic projection of information stored on a two-dimensional surface at the edge of space. This would make gravity, and perhaps space-time itself, emergent rather than fundamental. What we experience as the curvature of space-time might be a collective effect arising from the entanglement of quantum information on the holographic boundary. Loop quantum gravity has its own version of holography, where the quantum states of geometry on a surface encode information about the volume they surround. But this emerges naturally from the discrete structure of quantum geometry, rather than being imposed as an additional principle. Both string theory and loop quantum gravity have inspired new approaches to long-standing problems in physics. String theory has led to insights about black hole information, the nature of dark energy, and the possible existence of multiple universes. Loop quantum gravity has provided new perspectives on the measurement problem in quantum mechanics and the relationship between geometry and information. The two approaches have also begun to influence each other. Some string theorists have explored what happens when you compactify string theory in ways that produce discrete geometric structures similar to those in loop quantum gravity. Loop quantum gravity researchers have investigated whether their discrete spacetime might emerge from more fundamental degrees of freedom, similar to how string theory derives spacetime from string dynamics. Recent developments have suggested that both approaches might be different aspects of an even more fundamental theory. The emergence of spacetime from quantum entanglement, explored in both string theory and loop quantum gravity contexts, hints at a deeper level of reality where space, time, and matter all arise from pure information and quantum correlations. Experimental tests of these theories remain challenging because their most distinctive predictions occur at energies far beyond current technology. But both string theory and loop quantum gravity make predictions for phenomena that might be observable in the coming decades. Gravitational waves, cosmic ray interactions, and the cosmic microwave background all provide windows into the quantum gravitational regime. The mathematical complexity of both theories has also led to unexpected discoveries in pure mathematics. String theory has revolutionized areas like algebraic geometry and number theory, while loop quantum gravity has contributed to our understanding of knot theory and discrete geometry. These mathematical insights have value independent of their physical applications. As physicists continue to develop and test these theories, the dream of unifying light speed and gravity moves closer to reality, whether the answer lies in vibrating strings dancing through hidden dimensions, discrete loops weaving the fabric of space-time, or some synthesis of both approaches remains to be seen. But both theories have already transformed our understanding of space, time, and the quantum nature of reality. The journey toward quantum gravity has revealed that our universe might be far stranger and more wonderful than we ever imagined. Extra dimensions, holographic realities, discrete spacetimes, and emergent geometries challenge our most basic assumptions about the nature of existence. Yet these exotic possibilities emerge naturally from the mathematical requirements of consistency and the experimental facts of quantum mechanics and general relativity. The choice between string theory and loop quantum gravity is not just a technical decision about mathematical formalism. It's a choice about what kind of universe we live in and what kinds of explanations we find satisfying. As experiments become more precise and theoretical understanding deepens, we may discover that both approaches capture different aspects of a single, more comprehensive truth about the quantum nature of space-time itself. On September 14th, 2015, at precisely 9:51 Coordinated Universal Time, two detectors separated by 3,000 kilometers both registered the same impossible signal. For a fraction of a second, space itself stretched and squeezed by less than 1/10,000th the width of a proton. This tiny distortion carried a message that had traveled for over 1 billion years across the cosmos. It was the first direct detection of gravitational waves, and it opened an entirely new window into the relationship between light and gravity. The signal detected by the Laser Interferometer Gravitational Wave Observatory came from two black holes spiraling into each other in a cosmic dance of destruction. As these monsters, each containing the mass of about 30 suns, whirled around each other at half the speed of light, they created ripples in space-time that propagated outward at exactly the speed of light. This discovery confirmed one of Einstein's most audacious predictions and revealed a deep connection between light speed and gravity speed that had been suspected for a century. Gravitational waves and electromagnetic waves both travel at exactly the same speed through empty space, suggesting that this cosmic speed limit represents something fundamental about space-time structure. Imagine the universe as a vast ocean where two different types of waves propagate. Electromagnetic waves are like ripples on the surface, carried by fields that permeate all space. Gravitational waves are like sound waves traveling through the water itself, carried by the stretching and squeezing of space-time's geometry. The fact that both travel at the same speed hints they might be different aspects of the same underlying reality. Since 2015, gravitational wave observatories have detected dozens of black hole mergers, neutron star collisions, and other cosmic catastrophes. Each detection provides insights into how gravity behaves in the most extreme environments, where space-time is warped so severely that normal physics approaches its limits. One remarkable discovery came on August 17, 2017, when LIGO detected gravitational waves from two neutron stars spiraling together. Unlike black hole mergers, this collision produced a brilliant flash of light observed by telescopes worldwide. For the first time, astronomers could study the same event using both gravitational waves and electromagnetic radiation. The multi-messenger observations revealed something extraordinary. The gravitational waves and first light arrived at Earth within seconds of each other after traveling 130 million light-years. This provided the most precise test ever of whether gravity and light travel at the same speed over cosmic distances, confirming Einstein's prediction to within 1 part in a quadrillion. The neutron star collision created conditions so extreme that atomic nuclei were torn apart and reassembled into heavy elements like gold and platinum. The light showed distinctive signatures of these newly forged elements, revealing that such collisions are the primary source of heavy elements in the universe. We are literally made of neutron star collision stuff. Gravitational waves also provided unprecedented insights into matter under extreme conditions. Neutron stars are so dense that a sugar cube-sized piece would weigh as much as Mount Everest. The way these objects deform during collision depends on nuclear matter properties that cannot be reproduced in Earth-bound laboratories. Each gravitational wave detection tests general relativity in new regimes. Einstein's equations make specific predictions about signal shapes and frequency evolution, and every detection has matched these predictions perfectly. But physicists search for subtle deviations that might reveal new physics beyond general relativity. The cosmic microwave background radiation provides another crucial link between light and gravity. This ancient light, released when the universe was 380,000 years old, carries information about when quantum fluctuations in gravity were stretched to cosmic scales by inflation. These primordial quantum fluctuations in space-time curvature created tiny density variations throughout the early universe. As the cosmos expanded and cooled, these variations grew under gravitational attraction, eventually forming the galaxies we see today. The cosmic microwave background preserves a snapshot of these fluctuations when they first became visible. By studying patterns in the cosmic microwave background with incredible precision, cosmologists can infer properties of the universe when it was smaller than an atom. The statistical properties depend on fundamental physics, including dark matter nature, dark energy amounts, and inflation details. Some quantum gravity theories make specific predictions about the cosmic microwave background. If spacetime has discrete structure at the Planck scale, as loop quantum gravity suggests, this might leave subtle signatures in ancient light polarization patterns. String theory predicts additional fields that might have influenced primordial fluctuation evolution. Another cosmic laboratory lies near black holes. The Event Horizon Telescope has captured first images of regions around supermassive black hole event horizons. These images show shadows cast against bright backgrounds of hot gas spiraling inward. Shadow shapes and sizes depend on black hole mass, spin, and how gravity warps nearby space and time. The Event Horizon Telescope has also revealed how magnetic fields behave in extreme environments near black holes. Hot gas around these objects contains magnetic field lines that launch powerful jets of particles traveling at nearly light speed. Understanding jet formation requires combining general relativity with plasma physics and electromagnetic field theory. Gravitational lensing, light bending by massive objects, has become astronomy's most powerful tool for studying matter distribution and space-time nature. When light from distant galaxies passes near massive galaxy clusters, it gets bent and focused, creating distorted images that reveal dark matter presence. The bending amount depends on total lensing object mass, including ordinary and dark matter. By measuring background galaxy image distortions, astronomers can map dark matter distribution with extraordinary precision. This reveals that dark matter forms a cosmic web, providing scaffolding for galaxy formation. Some gravitational lenses create multiple images of the same background object. If that object varies in brightness over time, different images show variations at different times due to different light path lengths. This time delay effect provides another way to measure distances and test general relativity. Pulsar studies have provided some of the most precise general relativity tests. These rapidly rotating neutron stars emit radio wave beams, and their signal timing can be measured with incredible accuracy, allowing astronomers to detect tiny orbital changes caused by gravitational wave emission. The first indirect gravitational wave evidence came from binary pulsar PSRB, 1913+16 observations. This system has 2 neutron stars orbiting every 8 hours, and the orbital period decreases at exactly the rate general relativity predicts for energy loss through gravitational wave emission. Pulsar timing arrays, networks of precisely monitored pulsars across the galaxy, now search for gravitational waves with much longer periods than LIGO can detect. These waves might be produced by supermassive black hole binaries in distant galaxies, or even by cosmic strings, hypothetical one-dimensional space-time defects that might have formed in the early universe. The relationship between light and gravity revealed by cosmic observations points towards deep unity, underlying apparent physical phenomena diversity. Electromagnetic radiation and gravitational waves both carry information at light speed. Both can be lensed by massive objects, and both play crucial roles in cosmic structure evolution. Yet mysteries remain. Dark matter and dark energy nature, making up 95% of the universe, stays unknown. The precise cosmic inflation mechanism remains uncertain. Gravity's quantum nature continues to elude direct detection. But each new observation brings us closer to understanding how light and gravity are woven together in the cosmic tapestry, and how their unification might unlock the deepest secrets of space, time, and existence itself. Deep beneath the mountains of central Italy, in a laboratory shielded from cosmic rays by solid rock, scientists are attempting something that would have seemed impossible just decades ago. They're trying to detect the gravitational effect of a single photon, a particle of light so ephemeral that it has no mass and exists only when moving at light speed. This experiment represents the cutting edge of a new frontier where quantum mechanics meets gravity in ways that could finally reveal the hidden connections between light and space-time. The quest to probe quantum gravity through direct experimentation faces a fundamental challenge. The effects we're trying to measure occur at energy scales that are almost incomprehensibly large, or distance scales that are almost impossibly small. The Planck energy, where quantum gravitational effects become strong, is about 10 to the 19th billion electron volts. To put this in perspective, the most powerful particle accelerator ever built, the Large Hadron Collider, reaches energies of only 14 trillion electron volts. Building an accelerator capable of probing the Planck scale would require a machine larger than the solar system. But physicists are ingenious, and they've devised clever ways to search for quantum gravity effects using technology that exists today. These experiments don't try to recreate the extreme conditions where quantum gravity dominates. Instead, they look for subtle signatures that quantum gravitational effects might leave in more accessible phenomena. One of the most promising approaches involves quantum optics. the study of how individual photons behave in quantum mechanical systems. Researchers are developing experiments that could detect whether gravity affects the quantum properties of light in ways that current theories don't predict. These experiments use some of the most sensitive measurement techniques ever developed, capable of detecting changes smaller than 1 part in 10 to the 21st. In laboratories around the world, scientists are creating quantum states of light where individual photons are entangled with each other across large distances. When photons are entangled, measuring the properties of one instantly affects the other, regardless of the distance separating them. If gravity influences this quantum entanglement in unexpected ways, it might provide the first direct evidence of gravity's quantum nature. One particularly intriguing experiment involves dropping entangled photons in Earth's gravitational field to see if their quantum correlations change during free fall. According to general relativity, freely falling objects should experience no gravitational effects, but some theories of quantum gravity predict that the quantum properties of particles might be affected even during free fall. Other experiments are exploring whether gravity can create quantum superposition states of massive objects. In quantum mechanics, particles can exist in multiple states simultaneously until they're observed. But as objects get larger and more massive, maintaining these quantum superposition states becomes increasingly difficult. Some theories suggest that gravity plays a role in destroying quantum superpositions, providing a natural boundary between the quantum and classical worlds. Researchers have successfully created quantum superposition states of increasingly large objects, from individual atoms to molecules containing thousands of atoms. The goal is to push this boundary further, creating superposition states of objects large enough that gravitational effects become important. If these experiments succeed, they might reveal how gravity and quantum mechanics interact at the boundary between the microscopic and macroscopic worlds. Tabletop experiments are also probing the limits of Einstein's equivalence principle, the idea that gravitational and inertial mass are identical. This principle is a cornerstone of general relativity, but some theories of quantum gravity predict tiny violations that might be detectable with sufficiently sensitive measurements. The most precise tests of the equivalence principle use rotating masses and laser interferometry to detect differences in how different materials respond to gravitational fields. These experiments have confirmed the equivalence principle to better than 1 part in 10 to the 13th, but even more sensitive tests are being developed that might reveal violations at the level predicted by some quantum gravity theories. Atomic interferometry represents another frontier in precision gravitational measurements. These experiments use the wave nature of matter to create interference patterns with atoms, much like the interference patterns created with light waves. Atomic interferometers can measure gravitational accelerations with extraordinary precision and are sensitive to effects that might reveal the granular structure of spacetime. Some atomic interferometry experiments are designed to detect gravitational waves directly, complementing the laser interferometry used by LIGO and similar detectors. Atomic interferometers might be sensitive to gravitational waves with different frequencies than those detectable by laser interferometers, opening new windows into the gravitational wave universe. Space-based experiments offer unique opportunities to test the relationship between light and gravity. In the vacuum of space, free from atmospheric disturbances and terrestrial vibrations, scientists can perform experiments with unprecedented precision. The European Space Agency's LISA mission, planned for the 2030s, will create a gravitational wave detector with arms 5 million kilometers long, using laser beams traveling between 3 spacecraft to detect ripples in space-time. LISA will be sensitive to gravitational waves with much lower frequencies than ground-based detectors can observe. These low-frequency waves are produced by different types of sources, including the inspiraling of massive black holes in distant galaxies. and possibly even relics from the early universe, such as cosmic strings or phase transitions. Another space-based mission, the Laser Relativity Satellite, tests Einstein's theory by monitoring laser pulses bounced off reflectors placed on the satellite's surface. The mission can detect tiny deviations from the predictions of general relativity that might signal new physics or quantum gravitational effects. Satellite experiments are also testing whether the fundamental constants of nature truly are constant. Some theories suggest that quantities like the speed of light or the strength of gravity might change slowly over cosmic timescales. By comparing atomic clocks on satellites with those on Earth over many years, scientists can search for evidence of such changes. Underground laboratories provide unique environments for gravitational experiments because they're shielded from cosmic rays and other sources of noise. The Virgo gravitational wave detector in Italy and similar facilities use this natural shielding to achieve the sensitivity needed to detect gravitational waves from cosmic sources. Some underground experiments are designed to detect dark matter particles that might occasionally collide with specially designed detectors. While these experiments aren't directly testing quantum gravity, they're probing the nature of the dark matter that makes up most of the universe's mass and therefore shapes the large-scale structure of space-time through its gravitational effects. The search for dark matter also connects to quantum gravity, because many theories predict that dark matter particles should have specific properties related to the quantum structure of space-time. If dark matter consists of particles predicted by string theory or other quantum gravity theories, detecting these particles would provide indirect evidence for quantum gravity. Precision measurements of the cosmic microwave background radiation continue to provide indirect tests of quantum gravity theories. Future space missions will measure the polarization of this ancient light with unprecedented accuracy, potentially revealing signatures of quantum gravitational effects from the early universe. The cosmic microwave background preserves information about quantum fluctuations that were stretched to cosmic scales during inflation. If space-time has a granular structure at the Planck scale, this might leave subtle imprints in the statistical properties of these fluctuations. Detecting such signatures would provide direct evidence for the quantum nature of space-time itself. Particle physics experiments, while not directly probing the Planck scale, continue to search for phenomena that might be explained by quantum gravity theories. The Large Hadron Collider and future particle accelerators might discover extra dimensions, supersymmetric particles, or other exotic phenomena predicted by string theory and related approaches to quantum gravity. High-energy cosmic ray observations provide another window into extreme physics. When the most energetic cosmic rays interact with Earth's atmosphere, they create showers of particles with energies far higher than anything achievable in terrestrial accelerators. These events might reveal violations of special relativity or other signatures of quantum gravity at extreme energies. The Pierre Auger Observatory in Argentina and similar facilities detect these ultra-high energy cosmic ray events by monitoring the light they produce when interacting with the atmosphere. The highest energy events probe physics at energy scales approaching those where quantum gravitational effects might become detectable. Gamma-ray astronomy is also contributing to tests of quantum gravity. Some theories predict that the vacuum of space might have a granular structure that would affect the propagation of high-energy photons over cosmic distances. Gamma-ray telescopes can test these predictions by looking for energy-dependent delays in the arrival times of photons from distant gamma-ray bursts. The Fermi Gamma-ray Space Telescope and ground-based gamma-ray observatories have placed stringent limits on such effects, ruling out some simple models of space-time granularity. But more sophisticated theories make more subtle predictions that might still be detectable with future, more sensitive observations. Neutrino astronomy represents another frontier that might reveal quantum gravitational effects. Neutrinos interact so weakly with matter that they can travel across the universe almost unimpeded, carrying information about the most extreme environments where they were produced. High-energy neutrinos from distant sources might show signatures of quantum gravitational effects accumulated during their cosmic journeys. The IceCube Neutrino Observatory at the South Pole and similar detectors are beginning to map the high-energy neutrino sky. As these observations become more precise, they might reveal subtle effects that could point toward the quantum nature of gravity and space-time. Laboratory experiments with ultra-cold atoms are also probing the boundary between quantum mechanics and gravity. These experiments can create quantum gases at temperatures just billionths of a degree above absolute zero, where quantum effects dominate even for relatively large collections of atoms. Researchers are investigating whether gravity affects the quantum behavior of these ultra-cold atomic gases in ways that might reveal the quantum nature of the gravitational field itself. While these effects would be extremely small, the exquisite control possible with ultra-cold atoms might make them detectable. Quantum computing technology is opening new possibilities for testing fundamental physics. Quantum computers can simulate quantum systems that are too complex for classical computers to handle, potentially allowing researchers to explore the behavior of quantum fields in curved spacetime or other aspects of quantum gravity that are difficult to study experimentally. Some researchers are investigating whether quantum computers might be used to simulate black hole evaporation or other quantum gravitational processes. While these simulations wouldn't directly test quantum gravity, they might reveal new insights about how quantum mechanics and gravity interact. The development of increasingly sensitive interferometers continues to push the boundaries of what's measurable. Future generations of gravitational wave detectors will be even more sensitive than current instruments, potentially detecting primordial gravitational waves from the early universe or subtle effects predicted by quantum gravity theories. These advanced interferometers might also be used for other precision tests of fundamental physics. The techniques developed for gravitational wave detection are finding applications in searches for dark matter, tests of the equivalence principle, and other experiments that probe the foundations of physics. As experimental techniques become more sophisticated and sensitive, the boundary between what's theoretically interesting and what's experimentally feasible accessible continues to shift. Effects that seemed impossibly small just decades ago are now within reach of current or planned experiments. The search for quantum gravity effects through precision experiments represents a new kind of physics, where theoretical predictions and experimental capabilities are converging on phenomena that bridge the gap between the quantum and gravitational worlds. While we may not be able to build accelerators that reach the Planck energy, we're developing the tools to detect the subtle fingerprints that quantum gravity might leave on more accessible phenomena. Each new experiment brings us closer to answering fundamental questions about the nature of space, time, and gravity. Whether the answer comes from detecting the granular structure of space-time, observing violations of the equivalence principle, or discovering new particles predicted by quantum gravity theories, these experiments are pushing physics toward discoveries that could revolutionize our understanding of reality itself. What if everything you thought you knew about gravity was wrong? What if the force that keeps your feet planted on the ground, that guides planets in their orbits, and that bends light around massive stars is not fundamental at all, but merely an illusion arising from something far more basic and strange? This isn't science fiction. It's the cutting edge of theoretical physics, where some of the brightest minds are proposing ideas so radical they challenge our most basic assumptions about the nature of reality itself. The notion that gravity might be emergent rather than fundamental began to gain serious attention in the early 2000s, when physicist Eric Verlinde proposed that what we experience as gravitational attraction might actually arise from the statistical behavior of microscopic degrees of freedom associated with information and entropy. Imagine gravity not as a force pulling objects together, but as an entropic effect, like the tendency of a messy room to become even messier over time. Verlinder's approach draws inspiration from thermodynamics, the branch of physics that deals with heat, energy, and the statistical behavior of large numbers of particles. Just as temperature emerges from the average motion of molecules, even though individual molecules don't have temperature, Verlinder suggests that gravity emerges from underlying microscopic processes, even though those processes themselves aren't gravitational. The key insight comes from black hole thermodynamics, discovered in the 1970s by Jacob Bekenstein and Stephen Hawking. They showed that black holes have temperature and entropy, and crucially, that a black hole's entropy is proportional to the area of its event horizon rather than its volume. This was shocking because entropy usually measures the number of microscopic states a system can be in, and for ordinary objects, this number grows with volume, not surface area. The fact that black hole entropy depends on surface area suggests that the information content of any region of space might be encoded on its boundary rather than throughout its interior. This is the holographic principle, one of the most profound ideas in modern physics. It suggests that our three-dimensional reality might be a projection of information stored on a two-dimensional surface, like a hologram. If reality is indeed holographic, then the smooth space-time we experience might be an emergent property arising from the collective behavior of information bits on some distant boundary. Gravity, in this view, would not be a fundamental force but a macroscopic effect of underlying microscopic information processing, much like how the pressure of a gas emerges from the microscopic collisions of countless molecules. This idea has revolutionary implications for our understanding of space and time. In traditional physics, space and time provide the stage on which events unfold. But in emergent gravity theories, space and time themselves might arise from more fundamental entities, possibly related to quantum information and entanglement. Consider the possibility that space itself emerges from quantum entanglement between microscopic degrees of freedom. When quantum systems become entangled, they share correlations that can't be explained by classical physics. Some theorists propose that these quantum correlations, when they occur on a massive scale, give rise to the geometric properties we associate with space. In this picture, the distance between 2 points in space would be determined by the amount of quantum entanglement between the underlying degrees of freedom associated with those points. Regions with strong entanglement would be close together, while regions with weak entanglement would be far apart. The smooth geometry of space-time would emerge from the pattern of quantum correlations in the underlying quantum information. This entanglement-based view of space has found support in studies of the ADS-CFT correspondence, where researchers have shown that geometric properties of the bulk space-time are indeed related to entanglement properties of the boundary theory. When entanglement in the boundary theory increases, the corresponding region in the bulk space-time grows. When entanglement decreases, space-time can even disconnect, creating separate regions. The emergence of time is even more mysterious. Some theories suggest that what we experience as the flow of time might arise from the process of quantum decoherence, where quantum systems lose their coherence through interaction with their environment. As information spreads and becomes entangled with the environment, it creates an arrow of time that points from less entangled states to more entangled states. Another radical idea gaining attention is that gravity might be modified at very large scales in ways that could explain dark matter and dark energy without requiring new particles or exotic forms of energy. These modified Newtonian dynamics theories, known as MOND, propose that Newton's law of gravity breaks down when accelerations become extremely small, as they do in the outer regions of galaxies. Standard gravity predicts that stars in the outer parts of galaxies should orbit much more slowly than observed, leading to the inference that galaxies contain large amounts of invisible dark matter. But Mond theories suggest that gravity itself becomes stronger at large distances, naturally explaining the observed rotation curves without requiring dark matter. While Mond has had some successes in explaining galactic dynamics, it faces significant challenges in explaining other observations, such as the behavior of galaxy clusters and the cosmic microwave background. Most physicists remain convinced that dark matter exists, but Mond serves as an important reminder that our understanding of gravity might be incomplete, even at scales much larger than the quantum realm. The mystery of dark energy presents an even greater challenge to our understanding of gravity and space-time. Observations show that the expansion of the universe is accelerating, driven by some form of energy that fills all of space and has negative pressure. This dark energy makes up about 70% of the total energy density of the universe, yet we have no idea what it is. Some theorists propose that dark energy might be a sign that our understanding of gravity breaks down at cosmological scales. Perhaps Einstein's equations need to be modified to include additional terms that become important only when applied to the universe as a whole. These modified gravity theories could potentially explain both dark energy and dark matter as consequences of departures from general relativity. Another possibility is that dark energy arises from quantum fluctuations of the vacuum itself. Quantum field theory predicts that empty space should be filled with virtual particles constantly popping into and out of existence. These quantum fluctuations should contribute to the energy density of space, potentially explaining dark energy. The problem is that naive calculations of the vacuum energy give a result that's larger than the observed dark energy density by a factor of 10 to the 120. This is arguably the worst prediction in the history of physics, suggesting that either our understanding of quantum mechanics is fundamentally flawed, or there's some mechanism that cancels out most of the vacuum energy. Supersymmetry was once thought to provide such a mechanism, with the vacuum energies of particles and their supersymmetric partners exactly cancelling each other out. But the failure to discover supersymmetric particles at the Large Hadron Collider has made this explanation less plausible, leaving the cosmological constant problem as one of the deepest mysteries in physics. Some researchers have proposed that the cosmological constant problem might be solved by reconsidering the nature of space and time themselves. If space-time is emergent rather than fundamental, then the concept of vacuum energy might need to be completely reconceptualized. Perhaps what we call vacuum energy doesn't gravitate in the way we expect, or perhaps it's not a property of space itself, but of the more fundamental degrees of freedom from which space emerges. The holographic principle offers another perspective on dark energy and the accelerating expansion of the universe. If our universe is indeed a holographic projection from a boundary at spatial infinity, then the expansion of space might reflect changes in the holographic encoding rather than the dynamics of space-time itself. Recent developments in string theory have led to proposals that our observable universe might be just one of countless bubble universes in an eternally inflating multiverse. In this scenario, different regions of the multiverse could have different physical laws and constants, with our particular region being suitable for life only by chance. The multiverse idea provides a potential explanation for the apparent fine-tuning of physical constants. The strength of gravity, the mass of the electron, the rate of cosmic expansion, and many other parameters seem to be precisely adjusted to allow for the formation of stars, planets, and ultimately life. In a multiverse with different constants in different regions, we naturally find ourselves in a region where the constants permit our existence. While the multiverse concept is scientifically controversial because it seems untestable, it has profound implications for how we think about the relationship between physical laws and the structure of reality. If multiple universes with different laws exist, then the particular combination of light speed and gravity that we observe might not reflect deep truths about nature, but merely local environmental conditions. Another emerging idea is that both space and time might be discrete at the fundamental level, composed of indivisible units at the Planck scale. This digital physics approach suggests that reality might be computational in nature, with the universe operating like a vast quantum computer processing information about its own state. In discrete space-time models, the continuous geometry of general relativity would be an approximation that emerges at large scales. Much like how a digital photograph appears continuous when viewed from a distance, even though it's composed of discrete pixels. The fundamental entities would be bits of information, and the laws of physics would be algorithms that determine how this information evolves over time. This computational view of reality has led some researchers to investigate whether the universe might literally be a computer simulation, either natural or artificial. While this simulation hypothesis remains highly speculative, it raises profound questions about the nature of physical law and the relationship between mathematics and reality. The idea that light speed itself might be emergent represents perhaps the most radical departure from conventional physics. If space-time emerges from more fundamental information processing, then the speed of light might not be a fundamental constant, but rather a derived quantity that emerges from the statistical properties of the underlying computational process. In such theories, the constancy of light speed would be maintained not by any fundamental principle, but by the statistical averaging of countless microscopic random processes. This could potentially explain why light speed has the particular value it does, and whether it might vary under extreme conditions where the underlying statistical assumptions break down. These emergent theories also suggest new ways to think about the unification of physics. Rather than seeking a single equation that describes all forces, perhaps we should be looking for the fundamental information processing rules from which all physical phenomena emerge. The forces, particles, and space-time of conventional physics would all be different aspects of the same underlying computational reality. Quantum error correction has emerged as another important concept in these discussions. Just as classical computers use error-correcting codes to protect information from corruption, the universe might use quantum error, correcting codes to maintain the stability of space-time and the consistency of physical law. This perspective suggests that the robustness of physical law might not be a fundamental feature of nature, but rather an emergent property of quantum error correction mechanisms operating at the deepest level of reality. The precise values of physical constants and the specific forms of physical laws might reflect the optimal error-correcting codes for maintaining stable information processing in a quantum universe. As these radical ideas continue to develop, they're beginning to make contact with experimental possibilities. Some emergent gravity theories make specific predictions about deviations from general relativity that might be detectable in precision tests. Digital space-time models predict granularity effects that might show up in high-energy astrophysical observations. The holographic principle has led to concrete calculations that can be compared with experimental data, particularly in the context of black hole physics and the ADS-CFT correspondence. While we can't yet directly test whether our universe is holographic, the mathematical framework has already led to new insights about quantum gravity and the nature of space-time. These ideas represent more than just mathematical curiosities. They reflect a fundamental shift in how physicists think about the basic constituents of reality. Instead of viewing particles, forces, and space-time as fundamental, these theories suggest that information, computation, and quantum entanglement might be the true foundations of existence. Whether any of these radical ideas will ultimately prove correct remains to be seen, but they're already transforming our understanding of what's possible in physics and opening new avenues for both theoretical exploration and experimental investigation. The unification of light speed and gravity might require abandoning our most cherished assumptions about the nature of space, time, and physical law itself. As we stand on the threshold of a potentially revolutionary period in physics, These radical ideas remind us that nature might be far stranger and more wonderful than we've ever imagined. The universe might be holographic, computational, emergent, or something even more exotic that we haven't yet conceived. But whatever the truth turns out to be, the journey toward understanding it promises to reveal depths of reality that will reshape our conception of existence itself. We stand at the edge of a precipice, gazing into an abyss of the unknown that could contain the ultimate answer to existence itself. Behind us lies more than a century of revolutionary discoveries that have transformed our understanding of light, gravity, space, and time. Ahead lies the possibility of a final theory that could unite these concepts in a framework so elegant and complete that it would represent the culmination of humanity's quest to understand the cosmos. The dream of a theory of everything isn't just about satisfying scientific curiosity. It's about answering the deepest questions that have haunted human consciousness since we first looked up at the stars and wondered about our place in the universe. Why does anything exist at all? Why do the laws of physics have the particular forms they do? How did the universe begin, and how will it end? Is reality fundamentally mathematical, computational, or something else entirely? A successful unification of light speed and gravity would provide more than just mathematical elegance. It would unlock secrets that could reshape our understanding of black holes, revealing what happens to information that falls past the event horizon and whether these cosmic monsters eventually evaporate completely through Hawking radiation. It might tell us whether the Big Bang was truly the beginning of time, or merely a transition from some previous state of existence. Such a theory could revolutionize our understanding of consciousness itself. Some researchers have speculated that consciousness might emerge from quantum processes occurring in the brain, processes that could be influenced by the gravitational field created by neural activity. If consciousness is indeed connected to quantum gravity effects, then a theory that unifies these phenomena might provide insights into the nature of awareness, thought, and subjective experience. The technological implications could be staggering. A complete understanding of quantum gravity might reveal new ways to manipulate space-time itself, potentially leading to technologies that seem impossible today. We might learn to create artificial gravitational fields, bend space and time at will, or even access the energy locked away in the quantum vacuum. The leap from our current understanding to a theory of everything could be as transformative as the leap from classical mechanics to quantum mechanics and relativity. But perhaps most importantly, a unified theory would complete Einstein's vision of a cosmos governed by beautiful, comprehensible mathematical principles. It would show that beneath the apparent complexity and chaos of the universe lies a deep order that connects the smallest quantum fluctuations to the largest cosmic structures. The speed of light wouldn't just be an arbitrary limit, but would emerge naturally from the fundamental structure of reality itself. Yet the journey toward this ultimate theory has revealed just how strange and counterintuitive reality might be at its deepest level. The comfortable assumptions of classical physics, where objects have definite positions and properties independent of observation, have given way to a quantum world where measurement creates reality and particles can exist in multiple states simultaneously. The smooth, continuous space-time of general relativity might itself be an illusion, hiding a discrete, granular structure that operates according to rules we're only beginning to glimpse. Space and time, which seem so fundamental to our experience, might emerge from something even more basic, perhaps the quantum entanglement of pure information. The forces we observe, from the electromagnetic force that governs light to the gravitational force that shapes cosmic evolution, might all be aspects of a single unified phenomenon operating in dimensions we cannot directly perceive. The particles we think of as fundamental might be vibrating strings, loops of quantum geometry, or emergent patterns in a vast computational process. Even our concepts of existence and non-existence might need revision. The multiverse theories suggest that reality might be far vaster than our observable universe, containing an infinite number of regions with different physical laws and constants. In such a reality, our particular combination of light speed and gravity might be just one possibility among countless others. The pursuit of unification has also forced us to confront the limits of human knowledge and understanding. Some aspects of reality might be fundamentally incomprehensible to minds that evolved to navigate the classical world of everyday experience. We might be like two-dimensional beings trying to understand three-dimensional space, capable of detecting shadows and projections, but unable to fully grasp the underlying reality. Yet even if complete understanding proves elusive, the search itself has already transformed our world. The quantum mechanics developed in the quest to understand atomic structure has given us computers, lasers, and magnetic resonance imaging. General relativity, born from Einstein's attempts to understand gravity, enables the global positioning system and provides crucial corrections for satellite communications. String theory, despite remaining experimentally unconfirmed, has revolutionized mathematics and led to new insights about the deep connections between geometry, topology, and physics. Loop quantum gravity has provided new perspectives on the nature of space and time that might ultimately prove crucial for understanding the quantum world. The experimental techniques developed to search for quantum gravity effects have pushed measurement precision to previously unimaginable levels. Gravitational wave detectors can measure distortions smaller than 1/10,000th the width of a proton. Atomic clocks are so precise they would lose less than a second over the age of the universe. Quantum optics experiments can manipulate individual photons and create entangled states that span continents. These technological advances have applications far beyond fundamental physics. Precision measurement techniques developed for testing general relativity have led to improvements in navigation, communication, and timekeeping. Quantum technologies emerging from the study of quantum gravity might eventually lead to quantum computers capable of solving problems that are impossible for classical machines. The search for dark matter and dark energy has driven the development of ever more sensitive detectors and telescopes. These instruments are revealing the universe in unprecedented detail, from the cosmic microwave background radiation that preserves information about the universe when it was only 380,000 years old to the gravitational waves that carry messages from the most violent events in cosmic history. Each new observation provides pieces of the puzzle, gradually revealing the underlying patterns that connect light and gravity. The fact that gravitational waves travel at exactly the speed of light hints at a deep connection between space-time geometry and electromagnetic phenomena. The holographic principle suggests that information, rather than matter and energy, might be the fundamental constituent of reality. The emergence of quantum information science has provided new tools for thinking about these deep questions. Concepts like quantum entanglement, quantum error correction, and quantum computation are reshaping our understanding of how information flows through quantum systems and how complex phenomena can emerge from simple underlying rules. Some researchers now suspect that the universe might literally be a quantum computer, processing information about its own state according to the laws of physics. In this view, particles, forces, and space-time would all be different aspects of an underlying computational process, and the unification of physics would be equivalent to understanding the fundamental algorithm that governs reality. This computational perspective offers new ways to think about old problems. The fine-tuning of physical constants might reflect the optimal parameters for stable computation. The arrow of time might emerge from the irreversible flow of information through quantum systems. The apparent randomness of quantum mechanics might arise from the computational complexity of tracking all the correlations in a truly vast quantum system. But even as we develop these new perspectives, fundamental questions remain. Why does mathematics describe the physical world so accurately? Is this because reality is fundamentally mathematical, or because mathematical thinking is the only way minds like ours can comprehend complex patterns? Are the laws of physics discovered or invented? Do they exist independently of conscious observers, or are they somehow dependent on the act of observation itself? The anthropic principle raises equally profound questions about the relationship between physical law and conscious experience. The fact that the universe appears fine-tuned for the existence of complex structures like stars, planets, and life might be explained by the existence of multiple universes with different properties. But this raises the question of whether consciousness itself plays a fundamental role in selecting which universe we experience. Some interpretations of quantum mechanics suggest that consciousness might indeed play a crucial role in determining physical reality. If this is true, then a complete theory of everything might need to incorporate not just the laws that govern matter and energy, but also the principles that govern awareness and observation. The quest for unification has also revealed the importance of symmetry in fundamental physics. The electromagnetic and weak forces are unified through gauge symmetry. General relativity emerges from the requirement that the laws of physics be the same for all observers. String theory relies on supersymmetry to maintain mathematical consistency. These symmetries aren't just mathematical conveniences, they seem to reflect deep truths about the structure of reality. A final theory might reveal that all the apparent diversity of physical phenomena arises from the breaking of some fundamental symmetry, like different notes emerging when the perfect silence of the vacuum is disturbed. Yet symmetry breaking also introduces an element of contingency into physics. If the fundamental laws are symmetric, but reality as we observe it is not, then the particular way symmetry was broken in our region of space and time might be accidental rather than inevitable. This suggests that even a theory of everything might not predict all the details of our observable universe. The relationship between determinism and randomness in fundamental physics remains another deep mystery. Quantum mechanics introduces genuine randomness into the description of individual events, even though it makes precise statistical predictions about large numbers of events. Whether this randomness reflects fundamental indeterminacy or merely the limitations of our current understanding remains hotly debated. A theory that successfully unifies light speed and gravity might resolve this question by revealing whether quantum randomness is truly fundamental or emerges from some deeper deterministic process. Alternatively, it might show that the distinction between determinism and randomness is itself an artifact of our limited perspective on a reality that transcends both. As we look toward the future, several pathways toward unification seem promising. String theory continues to evolve, with new mathematical techniques revealing previously hidden connections between different versions of the theory. Loop quantum gravity is making contact with cosmological observations and black hole physics in ways that might soon lead to testable predictions. Emergent gravity theories are beginning to make specific predictions about deviations from general relativity that could be tested with future experiments. The holographic principle is leading to new insights about the nature of information and its relationship to space-time geometry. Quantum error correction is providing new tools for understanding how stable structures can emerge from quantum mechanical systems. The convergence of these different approaches suggests that we might be approaching a breakthrough comparable to the revolutions that gave us quantum mechanics and general relativity. But unlike those earlier revolutions, which could be understood largely through the work of individual geniuses, the coming synthesis will likely require the collaborative efforts of researchers from many different fields. The theory of everything, when it comes, might not look like what we expect. It might not be a single equation, but a vast computational framework. It might not predict specific outcomes, but describe the space of all possible realities. It might not answer our questions about the meaning and purpose of existence, but reveal that these questions are based on false assumptions about the nature of reality. Whatever form it takes, the ultimate theory will represent the culmination of humanity's greatest intellectual adventure. From the first humans who wondered about the lights in the sky, to the modern physicists probing the quantum nature of space-time, we have been engaged in a collective effort to understand our place in the cosmos. If light speed and gravity are indeed two languages describing the same underlying reality, then learning to speak their common tongue will be like achieving literacy in the fundamental language of existence itself. We will finally be able to read the universe as a book written in the language of mathematics, quantum mechanics, and geometry. The journey toward this understanding has already shown us that reality is far stranger and more wonderful than our ancestors could have imagined. Space and time are not fixed stages, but dynamic players in the cosmic drama. Matter and energy are interconvertible aspects of the same phenomenon. The act of observation can influence the reality being observed. The final theory, when it emerges, will likely reveal even greater wonders. It might show us how to transcend the apparent limitations of space and time, how to access information from the quantum vacuum, or how to manipulate the fundamental forces that govern reality. It might reveal connections between consciousness and physics that transform our understanding of what it means to be aware, thinking beings in a quantum universe. But perhaps the greatest wonder of all will be the simple fact that such a theory exists, that the universe is comprehensible to minds like ours, that the mathematical patterns we discover in our equations correspond to the deep structures of reality itself. In achieving a theory of everything, we will have completed the circle that began when the first conscious beings looked up at the stars and began to wonder why they shine. The universe, in learning to understand itself through us, will have achieved a kind of cosmic self-awareness that represents the ultimate triumph of intelligence over ignorance, of light over darkness, of understanding over mystery. And in that moment, the ancient dream of unification will be fulfilled, not just as a scientific achievement, but as a spiritual awakening to the profound interconnectedness of all existence.